Hello, and thanks for your interest in the subject of shaft alignment. This tutorial will discuss information that will hopefully assist anyone who designs machinery or couplings or drive systems, for anybody who is responsible for installing rotating machinery such as motors, turbines, pumps, fans, gears, compressors, and generators, for people who perform vibration analysis, and just about everybody who is involved in maintaining rotating equipment. So this information is intended for trades personnel, maintenance supervisors, vibration analysts, engineers, maintenance managers, and any interested operations personnel. The major topics that will be covered include the standard terms used to describe a misalignment condition, the one common design feature inherent in every flexible coupling, defining what shaft misalignment is, what are acceptable amounts of misalignment and what tolerances you should try to attain, and some statistical information on what the estimated time to failure of machinery might be when subjected to operate in a moderate to severe misalignment condition. When you hear people talking about misalignment, you hear the terms parallel misalignment and angular misalignment. Parallel misalignment is when the center lines of rotation of two shafts are parallel to each other but have an offset between the center lines. Angular misalignment is when the center line of rotation of one shaft is pointing at the center line of rotation of the other shaft. It is possible to have a pure parallel or a pure angular misalignment condition, but either condition is rare. Usually what you find is a combination of both a parallel and an angular misalignment condition. It is important to understand that shaft alignment, in its purest definition, is the process of aligning the center lines of rotation with each other, which are shown as the dashed red lines in the illustrations. Be aware that certain points along the length of the shaft may or may not be concentric with the center line of rotation of that shaft. In other words, you might have a run-out condition that could be overlooked or cause some grief when attempting to align the machinery. How to find and correct any run-out problems will be covered in another tutorial. The drawings of the motor and pump are shown here in a side view where you would need to correct the vertical misalignment by adding or removing shims from under the machinery feet. But the shafts could also be misaligned in the side-to-side or end-to-end direction. We live in a three-dimensional world, so shaft alignment is a three-dimensional challenge. Not only do we need to get the shafts aligned in the up and down direction, but in the side-to-side and end-to-end directions also. When you begin doing alignment on machinery, you will soon discover that getting the shafts aligned in the up and down direction is much easier than getting the lateral and axial alignment correct. Shaft misalignment is the deviation of relative shaft position from being in a collinear axis of rotation, and we measure these gaps or deviations at the flexing points or points of power transmission when the equipment is running under normal operating conditions. Now, that's quite a mouthful, but if you examine each part of the definition, hopefully you will see what I am trying to convey. First, the words collinear axis of rotation means that the axis of rotation of the motor is directly in line with the axis of rotation of the pump in this example. The words flexing points or points of power transmission are where the rotational forces from the motor are being transferred over to the pump. The caveat to this is that the deviations at the flexing points should be at or below certain values when the equipment is running. As strange as it may sound to some people, the shafts of certain drive systems will move to some other position than where they were at when they were at rest. Now, how and why machinery moves from offline to running conditions will be discussed in detail in another tutorial. For a long period of time, I was somewhat clueless about how couplings really worked. As you know, there are literally dozens of different types of couplings. I didn't want to have a set of alignment tolerances for gear-type couplings and a different set of alignment tolerances for a rubber tire-type coupling and yet a different set of alignment tolerances for a disc-type coupling. Why should acceptable alignment tolerances have anything to do with what type of coupling is used anyway? So I began to see if there is something common with all flexible couplings, and after a lot of study, I realized that there is one common feature that every flexible coupling needs to have, and that's this. For a flexible coupling to be able to accept both a parallel and/or an angular misalignment condition, it must have two flexing points in the design. So let's take a moment to examine what is meant by the flexing points in a coupling. Shown here are 6 radically different types of couplings, but they all share the same design feature. Every one of these couplings have 2 flexing points or flexing planes in their design. Some of the flexing points are very close together. Some of the flexing points are moderate distances apart, and some of the flexing points are a considerable distance apart. Since this is the common thread behind how all flexible couplings work, it makes good sense to describe the amount of misalignment that is occurring at the flexing points regardless of the type of coupling that is being used. Let's look at what is happening in more detail so you can understand why this is true. In the introductory tutorial, we discussed that one of the basic design principles of rotating machinery is that for a shaft to be stable during operation, it must have 2 radial bearings. We also discussed that it takes 2 shafts to make a drive system comprised of a machine that provides the rotational energy and another machine to do something useful with that energy. Ideally, we want the 2 shafts to be collinear. That is, we want the rotational center lines to be in line with each other. Since each shaft is contained in their own separate housing, it is possible for the shaft on the left to be low with respect to the shaft on the right. It is also possible for the shaft on the left to be high with respect to the shaft on the right. And it is possible for the shaft on the left to be pitched at an angle. Likewise, it is possible for the shaft on the right to be in this position, or it is possible for the shaft on the right to be in this position, or it is possible for the shaft on the right to be in this position. In other words, there is an infinite number of possible variations for the positions of either shaft, and therefore an infinite number of misalignment possibilities between the 2 shafts. For this discussion, let's say that we happen to have 2 shafts in this particular misalignment condition. We want to somehow link these 2 shafts together, right? To connect these 2 shafts together, we are going to install a link between these 2 shafts. This link is going to be called a coupling. For this to work, there needs to be 2 flexing points at each end of the coupling, right? What you need to understand is that when rotation starts, the shaft on the right, the coupling, and the shaft on the left are going to rotate on 3 different center lines of rotation. The flexing points on each end of the coupling must have the capability to transmit the torque from one shaft to the other, and we would like the rotation to be smooth and in some cases be capable of transmitting tremendous amounts of power. If you remember from the introductory tutorial, a shaft running at 1800 RPM will rotate 2.5 million revolutions in a day, which is 78 million revolutions in a month, and just shy of 1 billion revolutions in a year. Realizing that, it would seem to make sense that we should try to minimize the torture that the flexing points have to undergo. If we extend the center line of rotation of the shaft on the left toward the flexing point at the end of the shaft on the right, and show where the flexing plane is there, and conversely extend the center line of rotation of the shaft on the right toward the flexing point at the end of the shaft on the left, and show where the flexing plane is there, and look at the gap or deviation between the center lines of rotation at the flexing plane on the right side of the coupling, and look at the gap or deviation between the center lines of rotation at the flexing plane on the left side of the coupling, we now have a great visual image of the amount of misalignment that is occurring at both of the flexing planes. If we go back now and take a closer look at the misalignment condition on a simple motor and pump drive system, and zoom in on what's happening at the coupling, the dashed red lines represent the center lines of rotation of each shaft. Notice that there is both an offset and an angle involved. Let's say that we are going to install a flexible disc-type coupling in between the two shafts. Whatever misalignment is present, the flexing points in the coupling are going to have to accommodate the amount of misalignment that is occurring at each flexing plane. Shown here are the flexing points or flexing planes near the motor and pump shafts. If we then project the center lines of each shaft toward the other, we can now see what the gaps or deviations are at each of the flexing planes. Notice that the gap at the flexing plane on the motor is greater than the gap at the flexing plane on the pump. These two gaps now give us an indication of how accurately aligned we are in the up and down direction. But remember, not only do we have to be aligned within acceptable tolerances in the up and down direction, we also need to be aligned within the side-to-side direction. Now, let's take a look from above and again zoom in on the coupling area. As before, the dashed red lines represent the center lines of rotation of each shaft. Notice that there is both an offset and an angle involved in the side-to-side direction. Whatever misalignment is present in the lateral direction, the flexing points in the coupling are going to have to accommodate the amount of misalignment that is occurring at each flexing plane this way also. Here again are the flexing points or flexing planes near the motor and pump shafts. If we project the center lines of each shaft toward the other, we can now see what the gaps or deviations are at each flexing plane in the side-to-side direction. Notice that the gap at the flexing plane on the motor is greater than the gap at the flexing plane of the pump. These two gaps now give us an indication of how accurately aligned we are in the side-to-side direction. Here is the side view of the motor and pump showing the gaps at the coupling flexing points in the up and down direction. Here is the top view of the motor and pump showing the gaps at the coupling flexing points in the side-to-side direction. In this particular instance, in the vertical direction, the gap at the flexing plane of the motor is 6 mils and the gap at the flexing plane of the pump is 4 mils. In the lateral direction, the gap at the flexing plane of the motor is 3 mils and the gap at the flexing plane of the pump is 1 mil. Of the 4 gaps shown, 2 in the up and down direction and 2 in the side-to-side direction, where is the largest gap occurring? The largest of the 4 gaps is 6 mils, and it is occurring at the flexing plane of the motor in the vertical direction. We found that the largest gap was 6 mils at the flexing point on the motor side of the coupling in the vertical direction. The next piece of information we need is the distance between the flexing points. In this instance, let's say that distance is 4 inches. To determine the maximum misalignment deviation, divide the largest gap at the flexing points by the distance between the flexing points. So in this case, we take the 6 mil gap and divide it by 4 inches, which gives us a maximum misalignment deviation of 1.5 mils per inch. Is 1.5 mils per inch an acceptable amount of misalignment? Good question. What are acceptable alignment tolerances? This is the misalignment tolerance guide showing what is or is not acceptable levels of misalignment. On the x-axis of the graph is the speed of the drive system in thousands of RPMs. It makes sense to more precisely align machinery running at 10,000 RPM a little better than machinery running at, say, 1,800 RPM. On the y-axis of the graph is the maximum misalignment deviation expressed in mils per inch. What you want to do is get your drive system to be within the acceptable or excellent bands when your machinery is running under normal operating conditions. In our sample problem that we just examined, we determined that the 6 mil gap that was occurring over the 4-inch span between the coupling flex planes resulted in a maximum misalignment deviation of 1.5 mils per inch. If we find 1.5 mils per inch on the y-axis, then follow that over to the transition line within the acceptable region, we can then drop down to the speed at which this amount of misalignment is acceptable, which in this case is slightly over 4,000 RPM. What is important to understand is that there are 3 factors that affect shaft misalignment: the speed of the machinery, the maximum misalignment that is occurring at either flexing point in the coupling, and the distance between the flexing points. You shouldn't talk about misalignment in just mils of offset, and here's why. If we take 2 shafts that have 100 mils of misalignment and the flexing points in the coupling happen to be 1 inch apart, we have 100 mils per inch of misalignment. However, if we maintain the 100 mils of misalignment but separate the shafts 10 inches apart, we have 10 mils per inch of misalignment. If we again maintain 100 mils of misalignment but separate the shafts 100 inches apart, we only have 1 mil per inch of misalignment. In every case, there is 100 mils of misalignment, but 100 mils over 1 inch is different than 100 mils over 10 inches, which is different than 100 mils over 100 inches. The further apart you spread the flexing points in the coupling, the more forgiving that amount of misalignment becomes. This is why you should probably not talk about misalignment in just mils of offset. It depends on how far apart the flexing points in the coupling are. Here is a popular misalignment table used in industry. The column on the left is the speed of the drive system. There are 2 columns for excellent and acceptable angular misalignment expressed in mils per inch, and another corresponding set of columns for excellent and acceptable offset expressed in mils. What seems to be missing here is that the distance between the flexing points in the coupling is not being taken into consideration. For example, if we take the worst case offset number, 8 mils at 900 RPM, and do some math, an 8 mil offset over a 1 inch separation between flexing points is 8 mils per inch. An 8 mil offset over an 8 inch separation is 1 mil per inch, and 8 mils of offset over an 80 inch separation is only 1/10 of a mil per inch. That's a huge difference. That doesn't make much sense to me. What makes just about the same amount of sense is the best case scenario where you are attempting to achieve an offset of only 1 mil at 3600 RPM and above for excellent alignment. There are drive systems in industry running at 5 to 6,000 RPM with a 20 to 30-inch separation between the coupling flex planes. Attempting to achieve a 1 mil offset over 20 to 30 inches is a waste of time and effort. Likewise, if you are trying to align a cooling tower fan drive system running at 1800 RPM, where there is a 15 or 20 foot separation between the coupling flex points, and you are trying to get the offset less than 4 mils, is another waste of, well, hopefully you get the picture. There is another point of confusion when you start talking about angular misalignment. Notice here in this table, the angular misalignment is expressed not in degrees of angle, but in mils per inch. Exactly what angle are they talking about anyway? First, let's take a look at just a pure parallel misalignment condition. Here we have two shafts with a certain amount of offset between the center lines of rotation. If we observe what is happening between each shaft and the coupling, we notice that we have two identical angles at each flex point. Across the entire length of the drive system, there is the same amount of offset. Now, here is a more typical misalignment condition where there is both an offset and an angle involved. If we observe what is happening between each shaft and the coupling, as well as what is happening between the center lines of rotation of each shaft, we notice that we have three angles involved, none of which are the same angle. So, which angle are we going to talk about? Angle A, angle B, or angle C? Which offset are we going to talk about? Offset A, offset B, or offset C? Depending on who you talk to, you'll get different answers. For the majority of people I know who have a pretty good understanding of shaft alignment, it's angle C and offset B that they are typically talking about. However, when we usually discuss angles, we talk about angles in degrees of arc. Why, then, is the angular misalignment expressed in mils per inch? Because no alignment measurement system in existence is measuring angles. Everyone is measuring distance. Then we input specific dimensional information on a drive system. Angular misalignment expressed in mils per inch traces its source back to the face and rim alignment measurement method, where you measure the face of a coupling hub, typically over a 10-inch diameter, and you observe the change in distance between the coupling hub faces from the top to the bottom or from one side to another. But the face and rim alignment method is the subject of another tutorial, and the question of whether a minus 1.5 mils per inch or a plus 1.5 mils per inch means that the coupling hubs are closer together or further apart from the bottom to the top will be discussed at that time. A short while back, we were looking at the two gaps at the flexing planes in the coupling in the vertical direction. In the example shown, there was a 6 mil gap at the flexing plane at the motor and a 4 mil gap at the flexing plane of the pump. Now, how do you get these gap measurements? One way is to extract them from an alignment model. An alignment model is an exaggerated picture of the misalignment condition of a drive system. Not only can the positions of the misaligned shafts be shown, but additional layers of information can be superimposed on the alignment model to show offline to running machinery movement, boundary conditions, and external connection problems, along with how you can correct the misalignment condition. But that's getting way ahead of where we are currently at. Very simply put, alignment models show the misaligned condition in the up and down direction or in the side-to-side direction. So typically, two models are constructed, a side view and a top view. For now, let me show you an alignment model of a motor and a pump in the side view so you can see how and where to measure the gaps at the flexing points. A background grid is used to construct the alignment model. Two different scale factors are used as shown in the bottom left corner of the grid. Going from left to right, one scale is used to show where the positions of the outboard and inboard bolting planes of each machine are located and where the shaft measurements were taken. For this example, the scale factor is 2 inches per major division. A different scale is used in the up and down direction to exaggerate the misalignment between the shafts. In this case, it is 10 mils per major division or 1 mil per minor division. The solid blue lines represent the center lines of rotation of the motor and pump shafts. The X's represent where the inboard and outboard bolting planes are located on each machine. The two short vertical lines represent where shaft position measurements were taken with dial indicators or a laser detector system. The points here represent where the flexing planes and the coupling are located. The distance between the two center lines of rotation at the flexing plane of the motor shows the amount of misalignment gap there. The distance between the two center lines of rotation at the flexing plane of the pump shows the amount of misalignment gap there. The distance between the flexing points in this coupling is 4 inches. The top view alignment model shows that there is a 3 mil gap at the motor flexing plane and a 1 mil gap at the pump flexing plane. The side view model showed that there is a 6 mil gap at the motor flexing plane and a 4 mil gap at the pump flexing plane. The largest of these 4 gaps is 6 mils, so we divide that gap by 4 inches to obtain our maximum misalignment deviation of 1.5 mils per inch. Can a piece of machinery run in a misaligned condition? Sure it can. The question is, how long will rotating machinery survive running under various amounts of misalignment? The goal of accurate shaft alignment is to increase the operating lifespan of our machinery. After collecting failure information on hundreds of drive systems over the past several decades and examining the amount of misalignment that the machinery had been subjected to operate with, the estimated time to failure graph shows the relationship between the amount of misalignment our drive systems are subjected to and the rate of decay from the point where you begin to first see the signs of damage and wear to the point where a catastrophic failure is likely to occur. The x-axis shows the amount of misalignment in mils per inch, going from 0.2 of a mil per inch to 100 mils per inch. The y-axis shows the months of continuous runtime on a logarithmic scale. For example, if we had 2 new or recently rebuilt machines with new bearings and seals and shafts, and we had a 2.5-inch separation between the flexing points in the coupling, and we left 1/4 of an inch of misalignment between the shafts, what is likely to happen? Well, 250 mils over a 2.5-inch span is 100 mils per inch. If we ran a machine with 100 mils per inch of misalignment, somewhere around 1 month of continual operation, we will begin to see what we call initial machinery component decay. We will begin to see some damage to the bearings. We will begin to see some leakage at the seals. We will begin to see some wear in the coupling and begin to cyclically fatigue the shafts. Will the machines catastrophically fail in that time? Probably not. But if we continue to operate the drive system with that much misalignment, we will probably have a catastrophic failure somewhere around 20 to 30 months of continual operation. Not until we get down to 2 mils per inch of misalignment or better will it probably be something other than shaft alignment which causes the machinery to fail. The most common terms used to describe shaft misalignment is parallel misalignment and angular misalignment. Our drive systems can be subjected to operate with a parallel misalignment condition, or an angular one, or a combination of both. For a flexible coupling to be able to accept both parallel and or angular misalignment, it must incorporate two flexing points, or flexing planes, in its design. These flexing points are where the power is being transferred from one shaft to the other and are expected to work flawlessly for hundreds of millions of cycles. The less distress these flexing points have to endure, the more likely they will survive. The Misalignment Tolerance Guide provides a set of guidelines for acceptable amounts of misalignment for flexible couplings when the equipment is running under normal operating conditions. What is missing from this entire discussion is what the recommended guidelines are for rigid couplings. The reason no guidelines were discussed is because no guidelines exist for misalignment of rigid couplings. Apparently, it's assumed that it is not possible for a misaligned condition to exist on machinery that is rigidly coupled together. That assumption has been a demise of many a drive system. Well, thanks for your interest, and I hope you continue wanting to discover more about shaft alignment.